Well, it's my great pleasure to introduce Patrice Philippon from Institut de Mathématiques de Jussieu, and he will be speaking for us about generalizations of Schanuel conjecture.
Thank you very much. As mentioned, I will speak on generalization of Schanuel conjecture, and to be sure, this is a joint work with Christian Arbiertelin. And to be sure that of what we are speaking, this is bad. What's happened? So the conjecture is that if we take n complex number linearly independent of a q, then at least n of the number x1, xn, e to the x1, e to the xn are algebraically independent of a q. As you know, the conjecture is wide open, and the cases which are known are the case where x1, xn are algebraic numbers, which is Lindemann-Weierstrass theorem, and the case n equal 1, which is Hermite-Lindemann theorem. It was suggested by Cartier and promoted by Serge Lang, that the good frame for this problem of algebraic independence or transcendence should be the commutative algebraic groups. So the first case beyond the multiplicative group would be the elliptic curve, and then the abelian variety. And in this frame, we can state a naive analog of Schanuel's conjecture, saying that if we take an abelian variety defined over Q bar and U a point in the tangent space of A of C, then the transcendence degree of the field generated by the coordinate of U on X A of U, so the logarithm on the point, is at least the dimension of the smallest algebraic subgroup of A containing X P of U. This is known approximately like Schanuel's conjecture. It is known when U is defined over Q bar, but with the hypothesis that A is an abelian variety with complex multiplication. Now there is a much more precise and powerful conjecture which is due to Grothendieck, and which says that the transcendence degree of the field generated by the period of an abelian variety, defined over Q bar again, is equal to the dimension of its motivic Galois group. So there is a group which at the time was not well defined. And the most important part of the conjecture is the second one, is that the relation between periods come from an integration of algebraic cycle on powers of A. They define a torsor under the motivic Galois group. So that is, we have a group which acts on the Q bar Zariski closure of the point of defined by the period is a torsor under this group. That is, this is the orbit of one point. Well, it is to mention that if A is an abelian variety, then there are periods of different level. That is, if we integrate one form, again, cycles of one-dimensional cycles, then we get one forms, but we can integrate two forms, three forms, etc. And it is a fact that the R period, that is the period of the obtained by integrating form of degree R, are expressed as value of one of forms evaluated in one period. This will be useful to describe the Grothendieck conjecture. Thus, we have to consider the integration pairing between de Rham and Betti cohomologies. So I have written here this pairing. We have H de Rham, H1 Betti, and if we take a form, one cycle, then we have the integration. If we take now, if we choose basis over Q bar on the RAM cohomology, or a Q basis on the Betti cohomology, then we get a finite number of periods which are arranged in a matrix, which I have written here, omega A. This is a matrix of integration of the form on the cycles. So this can be viewed as an element of, in the case of our abelian variety, the dimension of the space of Durham space and Betti space, or 2G. So we can view this matrix as a 2G matrix and as an element of GL2G, because the determinant is not zero. Now I introduce an object which we will later compute in some cases, and which is put under assuming Grothendieck conjecture. This group is potentially the motivic Galois group I mentioned in the conjecture. So this group is the smallest algebraic subgroup of GL2G, so that the orbit GA times the period matrix GA, so the orbit of omega A under GA, is defined over Q bar. And if we assume Grothendieck conjecture, this group coincides with the largest subgroup leaving invariant the ideal of algebraic relation over Q bar between the entries of omega A. So you see from the previous slide, we have come to the pairing between differential forms and cycles of the whole dimension to just pairing between one cycle and one forms. Okay, let's see an example that we will see again later. The group GE of E, an elliptic curve. So as the abelian variety of dimension 1, we have an elliptic curve defined over Q bar. And if the elliptic curve has no complex multiplication, there is no relation, algebraic relation to deal with. So the group GE is just the full GL2. Now, if we have complex multiplication, then in this case, tau is a ratio of the two periods omega 2 omega 1 is a quadratic number. So this makes a linear relation between two periods, omega 1, omega 2. And the matrix of period, this is omega 1, omega 2, or the integral on the two free loops of the differential, holomorphic differential. And there are also the period of the differential forms of second kind, eta, derivative eta. And so we have eta 1, eta 2, the two other periods. And there is a relation I mentioned already, omega 2 minus 2 tau omega 1. And there is another relation which was discovered by Masser, or written down by Masser, which says that tau squared, modulus of tau squared, eta 1 minus tau eta 2 minus kappa omega 1 is 0 for some kappa in Q bar, which depend on the coefficient of the elliptic curve. So with this two relation now, we have constraint on the group GE, which is a group of matrices J in GL2, which leave invariant the ideal generated by these two linear forms. And some computation gives you the form of the matrix. This is B1, B2, three parameters. And the matrix is B1 minus B2 tau squared, B2, B1, what is it? Which is, so this matrix are invertible and they leave invariant the above ideal. If we want the form to be GM squared, what we have to do is to multiply our matrix, square matrix, diagonal matrix, sorry, not squared, diagonal matrix. We have to take the conjugate by this matrix. And we find the matrix we had before. We can see on this example what I mentioned at the beginning, not at the beginning, but a little before, that we have on the elliptic curve, we have the 0 period, the 1 period, which are omega 1, omega 2, eta 1, eta 2, and the 2 period, which is 2i pi. And we know that 2i pi can be expressed as a form of degree 2 in omega 1, omega 2, eta 1, eta 2. This is Legendre formula.
Patrice, I see there's a question in the chat. Wally, do you want to ask your question?
What is where is the question? Sorry.
Sorry, I was just asking when you defined this action of GA on the periods, when in the previous in 2 slides previously, what is the action explicitly?
Sorry, you mean the action of this matrix, or?
No, before this slide, when you first define yes, so the line in green over there. The next slide, I think.
Sorry, I missed your point.
I think the slide after this one, when you define GA, the group GA, and you say it's the smallest algebraic subgroup, such that the orbit GA dot omega A is defined over Q bar. What is the action explicitly? Is it given by acting on the coefficients of the forms?
So the action is that you take your matrix GA and you multiply on the left by the matrix omega A. Omega is the period matrix. And so and then you take one coefficient of omega A, you look at the corresponding coefficient of GA omega A, and this gives you the image of your period under the action of GA.
I see. Thank you. Thank you. Sorry.
Okay.
Sorry, if I may interrupt also, in this slide that you said that, so this GE is GL2 if there's no complex multiplication, there we are assuming the Grothendieck's period conjecture, right?
Yeah, actually, the definition of GA essentially assumes the Grothendieck conjecture.
Thank you.
Maybe the whole lecture is under Grothendieck conjecture.
I see. Okay. Okay. Thank you.
So we have seen that.
So unconditionally, it is a true statement for the motivic-Galois group. Without assuming any period conjectures.
Yeah.
If you said that about the motivic-Galois group, it's a true statement.
Yeah. Yeah. So the period conjecture implies that the orbit GA omega A is the Q-bar Zariski closure of omega A. So that is the important point. It describes the relation. It does not just give you the transcendence degree. Well, this is the dimension of GA, but it gives you also the shape of the Zariski closure, which is a torso. However, it has limitation. Well, actually, Grothendieck did not dwell much on this. First, it addresses to period of smooth Marietti and does not include logarithm of algebraic points. So, for example, we would like to consider curves with singular curves. And we also would like to consider logarithm of algebraic numbers like in Schanuel conjecture. And secondly, it assumes a variety defined over Q bar. And for these two reasons, it does not contain Schanuel conjecture. Because Schanuel conjecture, if you look at the GM, it will be defined over the field generated by the E of x1, E of xn, which are not assumed to be algebraic. So we can remedy this gap by first, for the first one, by considering first semi-abelian varieties. And for example, for singular curves, that would be generalized Jacobians, and introduce one motif to deal with the logarithm of algebraic points. And for the second limitation, we have André conjecture, so that I will mention later. So one motif M defined over a field K in containing C. Here I will assume that K is algebraically closed, so it brings some simplifications. So this is essentially an extension G of an abelian variety by a torus, which are defined over by K, over K. Such extensions, they are also called semi-abelian varieties, are parameterized by point Q1, Qs in the dual abelian variety A star of K. And they are inscribed in short exact sequence, where we have the torus on the left, on the right the abelian variety, and in the middle the extension, which is parameterized by, so the low group is parameterized by the Q1, Qs. And then, well, our motif may have points, marked points. So this is simply n points in G of K, which can be given also as the image of a morphism from Z to the N to G of K. Now I mention here for reference that a motif M is defined over K if the abelian variety A is defined over K, and the point Q1, Qs belongs to A star of K, and R1, Rn belong to G of K. So all the points are defined over K, the abelian variety is defined over K. And then we say that the motif is defined over K. So a couple of examples, more than a couple maybe. G, you may take A equals 0. So you have G, which is just the torus, Gm to the S. And you have R, which are a point in Gm to the S. So R would have S component. Or you can take S equal 1 on R1, Rn to be points in Gm. So you have now a torus of dimension 1. So this is for the case A equals 0. Now you can take the case G equals the abelian variety. So you don't have any torus. So S equals 0. And you just mark on your abelian variety n point R1, Rn. And you have the case that I hope is that if I go to the end of the lecture, I want to detail a little bit more. This is the third case, semi-elliptic surface. So this is semi-elliptic, means this is the abelian variety is an elliptic curve defined over Q bar. Q parameterize an extension by Gm, so S equal 1. And this belongs to E star of Q bar, so defined over Q bar again. And we have a 1 point, which is in G of Q bar. So S equal 1 or N equal 1 and the elliptic curve. We will compute the representation of the motivic Galois group, or more exactly the group we introduced, as explicitly as possible. So this repeats the definition we discussed just before. So now we have to write down the period matrix. Period matrix of an abelian variety, this is clear. of a one motive, we may put things down. So we take first the holomorphic differential form or form of the first kind on A. Then the second kind, so we note omega 1, omega g. Eta 1, eta g, this is a differential form of second kind, which are locally exact modulo holomorphic one. And for each GM, each factor GM, parameterized by the point QK, we introduce a different differential form which is invariant by translation, and which induce the invariant differential form on the corresponding factor of Gm to the S. And furthermore, we introduce exact form, that is df1, dfn, where the fi are functions, so zero form, such that the difference between the value at Rj and the origin O of G is 1 if I equal J and 0 otherwise. So this gives us a choice of basis of differential form. And now we have to take a basis of the Betti cohomology. So we have for A, gamma 1, gamma 2 G, the 2G loops, free loops on the torus. And delta 1, delta S are in each factor of Gm to the S loops. And we lift the gamma J to G, I denote by gamma J tilde. And we select path from the origin of G to Ri. So we can define with this generalized abelian and semi-abelian logarithm, which are for the generalized abelian logarithm of pi. This is the integral of the differential of the first kind, omega 1, omega g, and of second kind, eta 1, eta g. So this is why we call generalized, because there are also the basis for the differential form of second kind. And for the semi-abelian logarithm, we take the semi-abelian logarithm of the projection pi on A, and we add the integral of psi on the path from 0 to Ri of the psi qk corresponding to the factor. These are defined only up to periods of G, but we will put in the matrix the period already of G. So actually the field generated by the matrix, the coefficient of the matrix will not change. So with this, the matrix of period is this big thing. So you see we have put the differential form here on the bottom, and on the side we have put the loops. So here we have our path from 0 to the origin, from the origin to the point R1, Rn. Here we have the 2G loops on A, and we have the S loops on the torus. And here we have the differential form, so the exact differential form, df1, dfi. And with the choice we have made, this gives, the integral gives the identity matrix. These forms are exact, so when we integrate on loops, this gives zeros. Here we integrate the form differential, or the pullback of the form differential form omega 1, omega g, eta 1, eta g on loops which are verticals, which project on one point. So this gives 0. Otherwise, here we have the differential form which gives this matrix for A, so which is contained in our matrix for the motif. And then above, we have the point R1, Rn, and P1, Pn, the projection on A. And so we find here the logarithm of this P1, Pm on A. And if we take these two lines, this is the generalized logarithm, semi-elliptic logarithm I mentioned before, the semi-abelian logarithm.
So may I ask like a rather basic question? I just wanted to clarify something.
Yeah?
So when you define these generalized abelian periods, you have these 2G forms, which form a basis for the Durham cohomology on the previous slide. So is it like the first ones that you write down on the left-hand side, wouldn't they be usual periods? Since like eta J might not be holomorphic, but those would be cohomologous to some
Yeah.
something living in the actually the Durham cohomology or something like this, right?
To define them, we move the path away from the singularity.
I see. Where the like the singularity of the differential form, you mean, right?
Yeah. Yeah.
I see. So and this is not included in the usual periods, these 2G numbers that you have over there.
The 2G, you mean these numbers?
Yes, yes.
Yeah.
I see. So these are the classical periods as well, right?
Well, here this you mean the problem comes from the integration of eta j, which is
Yeah,
not all.
yeah.
Yeah.
I see.
But we can define this eta j by integrating from z and to z plus pi. And so we can move the singularities to get the okay.
I see. Okay. Thank you. Sorry. Thank you.
And here we have what I think is called the quasi-quasi period. So these are the period of the group G, this one plus this one. This is really the motif with the points, P1, Pn, R1, Rn. And here this is a GM. The GM, you have these forms, but as chosen, they restrict to the invariant differential form on each GM. So the integral on the loop d1 delta n is at each time 2i pi. So we have here an identity matrix multiplied by 2i pi. So example, I take back the example A equals 0, and we have GM. We have two possibilities. We can look at GM to the S, so a point in the torus of dimension S. And this is the first omega period matrix, omega M. We have the coordinate here of the point of our point R. Here on the opposite, we have put GM and put S point on GM. So log R1, log Rs are the logarithm of S point in GM. And I denoted this omega M and this omega M star simply because they are dual motifs, M. They are the period matrix of dual motif, M and M star. There is a notion of duality for motifs. And now if you take this matrix or that one, and you want to compute GM, you end up with this or that. And this is S plus S+1 cross S+1 matrix. On the first line, you have 1, A1, AS. And below you have 0, which account actually for S zeros. And we have here A0 times the identity matrix of size S. For the other one, you have a similar computation. But the condition is that the condition which makes that they live invariant, the element in this group live invariant, the ideal of relation between the period, is that this vector A0, A1, AS, first it belongs to Q bar cross, so the multiplicative part, cross Q bar to the S, and they satisfy the same Q linear relation as 2i pi log R1 log Rs. Thus, we conclude that Gm, in this case, Gm is the semi-direct product of Gm with Ga to the power d minus 1. D is the dimension of this space generated by 2i pi log R1 log Rs over Q. So now so we have seen the motifs and the period matrix. And now I come to the conjecture of Yves, which is a rather daring conjecture. It states that,
could I just ask the last thing you said in the previous slide?
yeah,
When you say, you mean the dimension as a vector space?
dimension of the vector space over Q.
So it's a linear dimension.
Yeah.
Okay.
Yeah. Yeah, for example, is the log R1, log Rs are linearly independent of a Q. And with 2i pi, this means we will have to. So if M is a one motif defined over K, and here we assume only K contained in C, not algebraic, then the transcendence degree over Q of the field generated over K by the period of M is at least the dimension of the group Gm. So you see, it's like in Schanuel conjecture. One thing is that it doesn't give you the transcendence degrees, the exact transcendence degree, like Grothendieck conjecture, which tell you this will be the dimension of this group. Here it says that the transcendence degree is at least. And you see in Schanuel conjecture, if you take x1, the conjecture is that the transcendence degree is at least n. But if you take x1, xn numbers at random, well, it's more likely that you will end up with a field of transcendence degree 2n. And here this is the same, that we have the field of definition of the motif, and we have the field of definition of the point, and this gives the lower bound for the dimension given by the motivic Galois group. But the assertion of Yves is that the transcendence degree of the field is not equal to this, but is at least this. Well, this conjecture is true, encompasses a lot of information on field generated by period. And for example, Christian Aquertelin has shown that it contains exponential, elliptic, semi-elliptic Schanuel conjecture. Rive has shown that it implies a strong form of the naive Abelian analog of Schanuel's conjecture mentioned at the beginning. Actually, the difference lies in the period. In the naive abelian analog I mentioned at the beginning, you just get information on the points, on the transcendent degree of the field generated by the point, and you just forget the period of the group of G. I think you can guess what is written on the top. I don't know. So we have seen the matrix omega M, the matrix of the motif, and we have seen that it has, accordingly to the choice of basis we have made, there are zeros and identity matrix, which so each zero or each one in the matrix reflect on the period, namely that the coefficient of the matrix is 0, equals 0. So we have a relation. So all these relations, which are of course trivial, must be considered and must be left invariant. And now a matrix which has a shape we saw, and we live invariant. I mean, a matrix which live invariant, the period matrix as we saw, must also have zeros and one. And actually, this is the general shape of a matrix living invariant, the trivial period relations, I would say. So this matrix, you see, it has a group of zeros on the left, whereas the period that was on the right. And there is some identity matrix here. And then we have the core of the matrix, which is the abelian variety, which must leave invariant the period of A. So this one belongs to GA, as mentioned here. And we have U star and sigma, which parameterize the unipotent part of the group. Yeah, here we find the determinant of A, because remember, we had 2i pi in the corner, and this 2i pi is just the determinant of the matrix omega A. So if A leave invariant the relation between omega and the 2i pi, we must have here this determinant of A showing. But of course, this is a reduction of the group with trivial relation. So the ideal of this matrix does not leave the ideal of relation in fixed. We have to restrict it, not all matrix. Now we know that for a matrix, for a group, subgroup, sorry, of the linear group, it can always be written as a semi-direct product of its unipotent radical, which are the element of GM with, so of this shape, but with A equals the identity, and here 1. And its reductive factor, which is just the GA. The group, the potential motivic gradual group for A. So Christiana Bertolin in 2003 has described the unipotent part of the group GM, or more exactly of the motivic gradual group, or the Mumford group in this case. So it is isomorphic. No, This is isomorphic to H1 of B cross H1 of Z, endowed with some group law that you may recognize. And so it introduced actually three objects which governs the geometry of the motif. We have first B, which is here. This is the smallest algebraic subgroup of AN cross A star S containing the point PQ. So in this, we have this matrix B. And then we have Z prime, which is the smallest subtorus of GM to the power NS, containing the image of the factor system of the associated extension of B by GM to the NS deduced from the Poincaré bundle. So that is from this embedding, we make a construction of a fiber bundle by gluing together Poincaré bundle of A and A star, so several copies. And Z prime is the smallest subtorus, so is the smallest subtorus such that the factor system is trivial. That is, this is the smallest subgroup which trivializes our bundle. And once we have done that, we define Z to be the smallest subtorus of GMNS containing Z prime. So containing the subgroup which contain all the factor system. And so when we restrict our bundle to B cross Z mod Z prime, this is a trivial bundle. Now we can take our point R, or 1Rn, and project it, since we have a trivial bundle, we can project it on the fiber. And then on the fiber, we can claim that we can decide that the point belongs to some quotient torsor, yeah. That is, we take Z, the smallest, so we can take Z any subtorus, but we take the smallest such that the fiber contains the point R. So important is B, Z prime, and Z. And Z prime governs Z. So the dimension of Z prime is governed by the abelian variety V itself. The theorem is as follows. The space of equation of Z prime. So Z prime is a subtorus of GM to the NS that we have here. And this map to the sum of the Q beta IK plus beta IK transposed, which is a sub-module of the homomorphism, the Q homomorphism of B to B star. So in particular, this means that the dimension of the torus Z prime is equal to the dimension of the Q vector space generated in this space by the element beta IK plus beta IK transpose. And what are these elements beta IK? They are constructed as indicated above by composition of homomorphism, gamma K and gamma I, which was actually deduced from the inclusion of B into AN cross A star S. This, if we project, if you compose this inclusion with the projection on the E's factor A of AN cross A star S, and you define gamma k star to be the projection on the case factor, the composition of J with the projection on the case factor of A star in this product, then you get your gamma I, gamma k, and this beta I is defined to be the gamma I transpose composed with gamma k. So now we come back to our example, and we had seen what's happened for an elliptic curve with complex multiplication in a previous example. And then we have a point which parameterizes an extension by GM. And we have a point which is marked on G. So for this, here is the period matrix I've written in large. Here we have the period matrix of the elliptic curve. Here we have the integral of first kind, second kind of the point P. And here we have the integral of the period of third kind of the point P again. And here this is just delta the loop in the fiber GM, so which gives the period 2i pi. And we have also the quasi-period of the extension G. So we know already that the shape of the matrix GM will be the matrix of A, the matrix of E, I mean, a matrix in GE, which we had computed in some example. And then we have the U star, the U, and the sigma. Here, this is the determinant of the matrix A. So now what do we do? According to the geometry of the one motive. So the geometry of the one motive will be described by B, Z prime, and Z. We list now with this, according to this geometry, we list all the polynomial relation with coefficient in Q bar between the period of M, which come from algebraic cycle on M, and on the product of M with itself. This polynomial relation generates an ideal I, whose locus of 0, Z of I, contains the point omega M. Omega M is the matrix, the period matrix. We list also a set of generators. So this is, of course, under Grothendieck conjecture. We list also a set of generator of the field Q bar of omega M. And we give a parameterization of the subgroup GM in GL4. So the subgroup which is invariant the ideal I. So I recall that the one motive is defined over Q bar, so we can use Grothendieck conjecture as mentioned. And the transcendence degree of the field Q bar is equal to the dimension of our group GM. Now to describe the group, we will present it as a semi-direct product of its unipotent part and reductive quotient. So the reductive quotient is GE. The reductive part will be UM. And in each case, we give a section F, which comes from GE to GM, and that identifies GE with an abelian, in our case, subgroup of matrices, because it is isomorphic to GM squared. So subgroup of matrices in GM, having trivial intersection with the normal subgroup UM. And those are called Levy subgroup of GM, and they are unique up to conjugacy by an element of UM. And so we have the description of the semi-direct product as usual. So we take this group, so we take this group. So the element of UM are described by the map row I introduced before, but with parameter identity U star sigma. And it is sent in GM by just taking the product of these two matrices. Alternatively, it can be defined by the product at the bottom. Okay. So I start with the dimension B equal 2. That means that the point P and Q are Q linearly independent. There is no, well, a subvariety which would contain the point PQ can be either of dimension 2 or otherwise it is of dimension 1, and this would be an isogenous to the elliptic curve, or of dimension 0. So in this case, we have the matrix. In the shape we have described a few slides before. And there is no relation because B is of the maximal dimension. There is no relation. The transcendence degree is 7, is generated by omega 1, eta 1. There is no omega 2, eta 2 because we're in the complex case, complex multiplication case. And then we have the point P, zeta P. We have the parameter of the group, Q, zeta Q. And we have the logarithm of third kind of P. So there is nothing more to say that this product is just the matrix I described before, AAU star, sigma. So you see there is a little change of variable to do to recover exactly the form we had before. But of course, if dimension of B is less than 2, strictly less than 2, then we will have relations. And what kind of relations? Those. So we have this set of relations which reflect, well, the first two. Well, I don't know. No. Well, the first two, well, this seems complicated, but this is to write the relation in terms of periods. And here we have the period omega 1, omega 2, eta 1, eta 2. But we have the quasi period, which are eta 1 q minus omega 1 zeta q, etc. And so, in fact, this is just 2I pi q zeta q with some transpose. So this is equal to 2I pi. The 2I pi simplify. And this really says simply that the point P and Q are related by some isogeny. So in this case, this is the case when dimension of B equal 1. We have the 2 points which are related. The last 4 gives that P for the 2 here, gives that P and zeta P is a torsion point. So P is a linear combination with alpha 1, alpha 2 rational of omega 1, omega 2. And this, you deduce that zeta of P has the same form with eta 1, eta 2, up to some algebraic number. The same relation, but twisted because of the twisted quasi-quasi period, is to say that Q is torsion. At the end, we have zeta Q, Q zeta Q. And we have the little one here, which says that the point R, or R tilde, is a torsion point or not. So if it is a torsion point, it will be a multiple of 2i pi. So the case dimension of B equal 1. In this case, P and Q are Q linearly dependent. But they are not both torsion, because if they were both torsion, the dimension of B would be 0. So we distinguish 3 cases in this step. That P and Q are Q linearly dependent, I said, but none is torsion. So we will have non-torsion, P torsion, or Q torsion, 3 cases. In the first cases, there is an isogeny. Here is the isogeny of E, which transform the point P in the point Q. So it's phi can be written phi I plus tau phi 2, and phi of P is equal to Q. And if we look at the matrix at the period P zeta of P, Q zeta of Q, the relation is just that that Q zeta of Q is equal to P zeta of P, multiply on the right by this matrix phi. Yeah, I like it. Okay. And so I denote, yeah, J is just a notation for this antisymmetric matrix. And now we have 3 subcases. That is the fact that phi plus phi bar is 0 or not 0 gives I mean, we can compute the element in Z prime in terms of the isogeny phi. And depending on the fact that phi is symmetric or antisymmetric, it's antisymmetric or not antisymmetric, we will have the dimension of Z prime equal 1 or 0. If phi plus phi bar is not 0, then the dimension of Z prime is equal to 1. And in this case, since Z prime is of dimension 1, we don't have to consider the case. Sorry, I am looking at the clock, and I think I am running. So I say in this case, we have this condition, the dimension of Z prime equal 1. And then there is no more space for R in Z mod Z prime, because Z prime is of dimension 1. GM NS is of dimension 1 also. So we have GM modulo Z prime, which is 0. And so any point will be torsion. So there is no two distinguished case or still distortion or not. And we end up with this matrix. So we have the lifting of our matrix as before. Here, lambda is introduced as a parameter, two parameters, and sigma is just a one-dimensional parameter. So we have three dimension here, 2 dimension for A, so that makes 5, and we have the 5 periods which generate the field. Yeah. So the discussion for the other case is quite similar. We have this case where now we have phi plus phi prime equals 0. Then the dimension of z prime is 0, as I tried to explain before. And we have to, now since the dimension is 0, there is space for a torsion point or not. So R tilde is not a torsion point. In this case, we have the dimension of z mod z prime equal 1. And we are back in the previous case, so we get the same matrix. When the point R is torsion, then dimension of z is equal to 0, because dimension of z prime is equal to 0, and the torsion point means z mod z prime is dimension 0. And so we compute and we find this representation. Then after that, we have the point P, a torsion point, but not Q. In this case, we see that we have to lift the group GE. We have to take into account that the matrix must leave invariant the relation between the periods. And so we have to introduce such a coefficient to get a lifting or a proper lifting. Then we have the case Q, a torsion point. So this is symmetric of what we have seen. And R is a torsion or not. And then we have dimension of B equals 0 finally. That is P and Q are torsion point. And in this case, if R is not torsion point, we have this decomposition. So the matrix lifted is more complicated. And here we just have a sigma in the corner. And then finally, the last case, we have no unipotent part, because everything is, the dimension of everything is 0. And we have only 2 periods to generate omega 1, omega 2. This is some reference. And this is the end of it. Thank you.